Hi everyone. Today we're going to talk about the central limit theorem for quantitative data, and so for sample means. Dr. Darbro will teach you the central limit theorem for proportions, categorical data later on. Today we're just going to be talking about the quantitative data. And so what we want to start out with is the sampling distribution model. And so it's kind of easy to think about the distribution for quantitative data, such as heights or weights or blood pressures, things like that. Let's say we went to your class and we found the height for everyone in your class. You could see those numbers. You can actually measure the heights. What you could do is summarize them by finding the average height, the average mean for your classroom. And then you could plot those heights onto a histogram. And so that's a nice way to think about the distribution for data as a whole. What becomes harder to think about is what the distribution of estimates would look like if you were to repeat the experiment over and over. And so if we were to repeat the experiment over and over, we would get different estimates each time, depending on the random sample that we get from the population. What you should do is note that the distribution of an estimate, such as a sample mean, is called the sampling distribution. And so what we want to think about is, let's say we have this population. Let's just say we're looking at the population of all high school students. What we can do is, let's say we go to your high school, and what we do is we go to each class. And so let's say we go, to your biology class. We take that sample and we find the average height from that biology class. And then let's say we go to the art class. So there's our other sample. And we find their average height. And you keep doing that, and you keep going to different classrooms, and you find all these different heights from the different classrooms. And so, if you were to plot these heights on a histogram, these sample means of these heights onto a histogram, what do you think this histogram will look like? And so that's what we want to talk about. We want to think about if you go out and you take different random samples from the population and find different sample means, if you were to plot these sample means, what would that histogram look like? And so what we have is called the central limit theorem. This theorem is going to be very important for us and for sampling distributions. What it does is tells us the shape, the center, and the spread of a sampling distribution. And so what the central limit theorem is that it says that the distribution of sample means has an approximate normal distribution no matter what the distribution of its original data looks like, as long as the sample size is large enough and all the samples have the same size. And so what this is saying right here is that if you, let's just go back to the next slide. If you were to take these sample means and you made a histogram, their shape would be approximately symmetric, and the larger the sample size will get, the more samples that you take, the closer to the normal distribution these estimates will be. And so that's what this central limit theorem is trying to tell you right here. And so if we look at this for quantitative data, it's going to tell you three things. The first thing it's going to tell you is that the mean for your sample mean x bar is always going to be the population mean mu. The standard deviation is going to be the population standard deviation divided by the square root of your sample size. And then the shape is going to be approximately normal if you have a random sample, and you should take note that the sample size is large enough. And so how large is enough? Well, that depends on who you're talking to. But you want a very large sample. However, we look at means. Means vary, and so there's really no set in stone of how large a sample should be. Some people will say at least 30, but it's not set in stone. But these are the three main things that the center limit theorem talks about when you talk about quantitative data and you're looking at the sample means. And so, in the previous videos, you should have learned when we talked about the normal distribution, the 68, 95, 99.7% rule. That's coming back to you guys. Yay for that. And so what we want to do is look at an example. Let's say we had a random sample of 200 college women with a low BMI, and it was reported that they had a mean weight of only 140 pounds. And let's say for all college women out there, the mean is 143.74 pounds with a standard deviation of 51.54. And so we want to think about, does the mean weight seem very low? And so we can use the 68, 95, 99.7 to see, is this mean weight particularly unusually low for this type of data right here. And so what you should do is pause the video, write down our sample size, write down the sample mean, the 140, write down the population's mean, the 143.74, with the standard deviation, and let's see, is this mean weight unusually low? And so what we want to do is that, let's just write down, we had a sample size n equaled to 200. There's our sample size. It said that for the sample of 200 women, their average weight was 140. And so right here, here's our sample. Now let's talk about the population. And so for the population, it said that the mean weight for all college women was 143.74 and a standard deviation of 51.54. And so there's our population right here. And so what we want to do is, if we're looking at the center limit theorem, let's first talk about the mean for x bar. And so the mean for x bar is always the population mean. And so here the population mean is 143.74. And so there's your mean for x bar. The next thing it told us was the standard deviation for x bar. It's this population standard deviation divided by the square root of your sample size. And so what you want to do is take your standard deviation, 51.54, divided by the square root of the sample size, 200. And I'm going to just put the amount over here. It's kind of messy looking. You can figure it out. And so if you take the standard deviation divided by the square root of your sample size, you should get 3.64. And so there's our standard deviation for our sample mean x bar. And then we're just going to have to say for the shape, this is large enough. We did take a random sample, and so the shape is approximately normal. And so what we want to do now is, here let's just write down the mean and standard deviation that we found for x bar just one more time. We want to know, is their sample mean that we got, that 140, unusually low? And so to do that, think back to the 68, 95, 99.7%. If we talk about 68%, we were talking about one standard deviation from the mean. And so we're still looking at the normal curve. Here the mean is at 143.74. And so 68% was one standard deviation. And so let's find that percent right here. And so to find that, you take the mean, 143.74, plus and minus. It's one standard deviation, and so 1 times the standard deviation, 3.64. And so you want to add and subtract 143.74 minus 3.64, and then you're going to take 143.74 plus 3.64 and find those two values there. And so if you add and subtract, I believe you're going to get 140.10, and you should get 147.38. And so there's your 68%. And so 68% of college women have a BMI, or not BMI, a weight between 140 and 147. Next, let's find the 95%. And so here you're going to take the mean weight, 143.74, plus or minus. 95% is 2 standard deviations, and so 2 times your standard deviation, 3.64. And so you're going to also add and subtract. And I believe if you do that, you should get 136.46 and 151.02. And so here, 95% of college women have a weight between 136.46 and 151.02. And so lastly is the 99%, 99.7%, excuse me. And so 99.7% is 3 standard deviations from the mean. And so you're going to take your population mean, 143.74, plus or minus 3 times the standard deviation. And so you want to find those two values there. And so if you do, I believe you should get 132.82 and 154.66. And so what you should do is write these numbers. And so just write these values right here down. Here's our 68, our 95, and 99.7% ranges here. And so here I made you a nice graph. You don't have to look at my drawing. I'm sorry, the next problem you're not going to be so lucky. And so if we look at this right here, here's our 68%. Here's our 95. Here's our 99.7. We were told that the sample mean was 140. And so here's our 140 right here. And that's within our 3 standard deviations. It falls in 2 standard deviations. And so what you can say is that no, this is not unusually low. It's within 3 standard deviations. Remember, anything outside 3 standard deviations is unusually large. It's usually an outlier. And so if your sample mean falls within 3 standard deviations, it's perfectly fine. It's not unusually low or high, large or small. It's perfectly right there with the rest of the people, the rest of the data. And so here, what we can say is no, this is not unusually low for a mean weight. And so here again is what I just talked about. And so this is how you can decide if something's is actually unusual when you talk about the central limit theorem. Let's take another example. And so, scores on the ACT have a normal distribution with a mean of 20.6 and a standard deviation of 4.8. Let's say we take a random sample of 36 seniors and they report that their mean score is 25. Does the mean score seem unusually high to you? Well, we can do exactly the same thing. Let's see if their mean score is within 3 standard deviations or outside of 3 standard deviations. And so, and I should have said this first, you should have paused the video and wrote down the mean and standard deviation. I guess I'm getting a little excited here. And so we were told that the population mean was 20.6. The standard deviation was 4.8. We had a sample size of 36. And we want to see if their mean score of 25 was unusually high. And so again, let's go back to the central limit theorem. And so the mean for sample mean x bar is the population mean. And so that's going to be 20.6. Standard deviation for x bar is going to be the population standard deviation, 4.8, divided by the square root of our sample size, 36. And so I believe if you calculate that, you get 0.8. And then we had a random sample. This is a fairly large sample size, and so the shape is going to be approximately normal. And so you could find the 68, 95, but really the only thing you need to find is the 99.7%. You find that, and that's going to tell you if the mean is going to be, their mean score is unusually high, or it's just right there with the rest of the other mean scores there. And so let's find the 99.7% range. And so you're going to have the mean 20.6 minus 99.7 is 3 standard deviations. And so 3 times the standard deviation for x bar, 0.8. And then you're going to take the mean 20.6 plus 3 times 0.8. And so I'll just give you a minute to figure those out. And so if you figure those out, you should get 18.2 and 23 for your values. And so right here, here's our range for the 99.7%. And so let's just if you look at this, does their sample mean 25 fit between 18.2 and 23? No, it doesn't. And so what you could do, and what you can say, if you wanted to, you could draw the normal distribution. And so here's our mean. Our mean was at 20.6. 99.7% was 18.2 to 23. They had a mean score of 25. It's outside of this range right here. And so it's definitely going to suggest that the mean is high unusual. It's outside of 3 standard deviations. And so this is how you can use the central limit theorem using the 68, 95, and the 99.7% rule. And so if something's unusual, it's going to be outside of 3 standard deviations. It's going to fall outside of the 99.7%. And so you should just go back, look through these problems, and try them yourself. The next video is going to talk more about the center limit theorem and how we can use the z-score to find probabilities.